Hey guys, hope everyone's doing well. Today what we're going to be looking at is volume, and so we're going to call this volume 1. Same as last lesson where we were looking at surface area of different objects. This is going to be a little bit of a recap of things that you've probably done in the past. So we'll start off just talking about what exactly volume is. We'll look at an example, talk about some general rules, and we'll go from there. So when we're talking about volume is just a measure of how much space an object takes up. So for example, if I was talking about a cupboard, cupboard is a form of a rectangular prism. Typically we could work out how much volume or how much space that object takes up in a room. So we'll jot down firstly a few notes. So our subheading is going to be on volume, and we'll jot down a few dot points. So firstly, that first statement that we made, volume is a measure of how much space an object takes up. Now when we express volume, we have to use units of length, so meaning millimeters, centimeters, meters, kilometers, but because we're dealing with a three-dimensional object, it has to be cubed. So we will say the units that we use for volume are millimeters cubed, centimeters cubed, meters cubed, kilometers cubed, and we'll just say etc. So there'd be a few other ones there depending on how big or small we want to go. So the general rule whenever we're working out the volume of something is that it's quite easy whenever we have some sort of a prism or a cylinder, as we talked about the other day. They're different. A prism or a cylinder, because essentially if we can cut that shape up and have an identical cross section all the way through that shape, essentially our rule is no matter what, it is always the area of the base of our shape times by the height. So we'll write that down. The general rule is, or the general rule for volume is volume equals the area of the base times by the height of our prism. So what I mean by that is that no matter what our shape is, or no matter what our prism is, so let's say, let's start off nice and simple. So let's say we've got a rectangular prism. So I'll get my mad drawing skills happening again. If we wanted to find the volume of this shape, it would be the area of the base of our shape, even though it's on its side. We'll say that this is the shape, and the reason for that is because if we were to cut it across like this, or this, or this, the shape would be the same. It would be a square each time. It would be the area of the base, which is our highlighted bit, times by the height. So even if we had a different shape, let's say like so, Now this of course would be a triangular prism. We would have the area of our base of base times by our height. Now the reason I've got it on its side, so it's the area of the base is on the top or the bottom, they're the same area, as opposed to on the side like in our first rectangular prism, is that if we cut it across this way now, each time we would get the same shape and it would be a triangle. I'll do one more just example for you. So let's say we had this. This is going to test me out here. Oh geez. Oh, look at me go. So here we've got a hexagonal prism, so it gets its name from the hexagon shape for its base. We would have the area of its base. Actually, I might mix it up this time. I might do the bottom. So the area of the base again times by the height. So just to give you a few examples there. Now if you can remember this rule, I feel you can't really go wrong. Obviously things get a little bit difficult when we're not dealing with an object that has the same cross-sectional area through it. And so if I were to give you an example of a shape like that, that would be something like a cone, where if we cut it across here, we'd get the same shape, which would be circles, but the circles would be getting bigger each time. If you cut it down here, it's only going to be very little as opposed to the top. Similarly, if you cut it down here, they're going to be all different sizes. So this is not one of the shapes that we're talking about where this rule would apply of the area of the base times by the height. And I can't say for sure, but what you'll probably find out at some point is that cones have their own little formula that you would have to use to work out the volume. Alright, so I'm going to do a worked example with you. So we've got worked example. And our worked example says, calculate the volume of the following 3D shape. Now, shape looks like this. It is, of course, a triangular prism. We've got measurements of, I'll do it in red, 20 centimeters down this way. Got a measurement of 10 centimeters this way. And from here to here, we'll say that's 7 centimeters. So if we wanted to find the volume of the shape, we'd say volume equals area of the base times by the height. And the area of the base is for a triangle. So if I go through and highlight it, this is our base down here. we're dealing with a triangle. Area of a triangle is 1/2 times B times H. So we've got 1/2 times by 10 times by 7, which would be 35 centimeters squared. Now, if you're wondering about where these squares and cubes come from, what we can actually say is that we've got 10 centimeters times by 7 centimeters here. So this centimeter and this centimeter here, when we times centimeter and centimeter, we're going to get centimeters squared. And so this gives you a little bit of an insight as to how we get volume in cubed units, because our volume is the area of the base, which is 35 centimeters squared, times by the height, which is 20 centimeters. Similarly, we got our centimeters squared, our centimeters over here. So centimeters squared times centimeters, centimeters cubed. Now 35 times 20 is 700 centimeters cubed. Easy. Now, I'm going to do another example with you, because what we actually find when we're dealing with cylinders is that the process in which we find the volume of a cylinder is very similar to our prisms. So we've got another worked example. And our cylinder, or our question reads like this: calculate the volume of the cylinder correct to 2 dP. So here's our cylinder. So our cylinder has measurements of 50 millimeters high, and we'll say it has a diameter of 17 millimeters for the base. So we start off with our rule. Volume equals area of the base times by the height. Then the area of our base is equal to this shape here, which is circle. Now we're all pros at circles, and we know that the area of a circle is pi r squared, which is going to be pi times by. Now here we've got a diameter of 17 centimeters, so we have to halve it, or divide it by 2 squared. Put that in our calculator, and we've got pi times by 17 over 2 squared is 226.98 centimeters squared, dealing with area. And now we're going to sub it into millimeters squared. Don't get caught out. Now the volume will be the area of the base, which is 226.98 millimeters squared, times by the height, which is 50 millimeters squared, times by 50, and we get an answer of 11349. And in this case, it's a round number, but because they've asked us to 2 dP, we better go 0.00. And it's going to be millimeters cubed. So hopefully you can see here, guys, that whenever we're dealing with an object and it's got the same cross-sectional area all the way through it, which means it's got the same shape at both ends and it remains constant all the way through our shape. Our rule's pretty simple. It's just the area of the base times by the height. Now the next thing that volume leads itself toward is the idea of capacity, and it will be our next subheading, capacity. So when we're talking about capacity, typically we're talking about holding stuff, in particular liquids. So if we're talking about the capacity of a water bottle or something like that, we're talking about how much liquid we can put inside that container. So essentially it's a measure of how much volume we have on the inside of our object. So how much volume we have inside of our water bottle. Now the tricky part about capacity is that often we have to do a bit of converting because we're dealing with units of length when we're working out the volume of something, and this is often what we're given. But capacity deals in a different unit, which is mils, litres, kilolitres, and so forth. So before we get too far into that, let's just write down what capacity actually is. So capacity is a measure of how much liquid can be held by an object. And it's measured in, capacity is measured in mils, litres, kilolitres, etc. And when we're dealing with millilitres, so lowercase m, capital L. Millilitres, litres, capital L, and kilolitres, which is a lowercase k and an uppercase L. Now for our conversions, we need to know that 1 mil is 1 centimetre by 1 centimetre by 1 centimetre. So 1 centimetre, 1 centimetre, 1 centimetre equals 1 mil. Now, I'm sure you guys all remember that 1 litre is equal to 1,000 mil. Now, what I don't want you to think is that if 1 centimetre by 1 centimetre by 1 centimetre is 1 mil, what I do not want you to think, so I'm going to draw a big cross through it before I even draw it, is that 1,000 centimetres by 1,000 centimetres by 1,000 centimetres is 1,000 mil. Because we're timesing these numbers, it doesn't work. So look at that. Disgusting. Get rid of it. We don't want it in our books. So what we're actually going to find is that 1 litre is made up of 1,000 centimetres cubed, and a 1,000 centimetres cubed is actually made up of 10 centimetres by 10 centimetres by 10 centimetres. Jeez, that's a dodgy cube. Alright, so 10 times 10 times 10 is 1 with 1, 2, 3 zeros. And sure enough, 10 times 10 times 10, 1,000 centimetres cubed, which is 1 litre. So we will say that a 10 by 10 by 10 centimetre cube is 1 litre of whatever liquid it is that we're talking about. So if we were going to complete some conversions, we've got a worked example. And worked example says, complete the following conversions. So for this first bit, we've got 50 mil is how many centimeters cubed? So let's go back to our conversion. Did we not really write it down? Alright, we'll say 1, maybe we could fix this up. Now I apologise, I know you guys have already written this down. So 1 centimetre cubed is 1 mil, 1,000 centimetres cubed is 1 litre. So we've got 50 mil. So essentially what we're going to be doing is operating backwards. So we've got 50 mil. So 50 mil will be 50 centimetres cubed. Nice and easy to kick us off. B, we have 150 mil equals however many litres. So in order to work this one out first, we know that, alright, off to the side, 1 mil equals 1 centimetre cubed. So 150 mil will be 150 centimetres cubed. Oh, I'm taking you down a track we don't even need to go. So we'll say 1 litre is 150 mil. So what we're going, no, what am I doing? 1 litre is 1,000 mil. So we've got 150 mil out of 1,000 mil per 1 litre, which is 0.15 litres. We got there in the end, we did it. Now finally, we've got 0.35 litres is however many centimetres cubed. Now we get to get into it. So we know that 1 litre, or we might start off by saying 0.35 litres is how many mil? So it's 0.35 times by 1,000, which is 350 mil. Now we know that 1 mil is equal to 1 centimetre cubed, and therefore it would make sense that 350 mil would just be 350 centimetres cubed. Easy. Alright, so from here on, guys, I think hopefully you should be ready to go on and do a few questions by yourself. The thing I want you to take away from this is the golden rule, that volume is the area of the base times by the height. Now next lesson, we'll be looking at a few different shapes. So just having a quick look, we'll be looking at spheres and some composite shapes. But for now, all you need to know is volume is area of the base times by the height. And you should probably remember a little bit of capacity as well. 1 centimetre cubed is 1 mil. 1,000 centimetre cubed is 1 litre. Alrighty guys, I will see you next time.